So we're reviewing for organic chemistry and chemistry today, and you have a test going on probably pretty soon, which is probably why you're watching this. So here's an equation. This is representing a chemical reaction. And so the idea here is that if you look at the arrow, anything before the arrow is what you start with, and anything over here is what you end with, or what you produce. So the hydrogen molecules are what we start with, so that's reactants. So that's this one. Whoops, sorry. And the water molecules are what you produce, because it's on this side of the arrow. So those are products, so that's here. An atom that has 9 protons, 8 neutrons, and 10 electrons is, okay, first of all, neutrons are neutral, and so if we're trying to figure out charge, we can get rid of the neutrons. So I would write it like this, 9 protons. Proton is positive, so that's 9 plus, and then 10 electrons. That would be 10 minus. So if you take 9 plus and 10 minus, and you balance out each one, you're going to balance one of these with one of these, one of these with one of these. They'll neutralize each other. In the end, you're going to actually have one leftover negative. So that will have a positive, that will have a -1 charge. Anything with a charge is an ion. If it started as one atom, it certainly wouldn't be a molecule. It's not uncharged because it's got a -1 charge. And a protein's made out of a lot of atoms. And a protein can be an ion, but this one's not because it says an atom. A blank forms when two atoms share electrons. Okay, this is a really, really important one. The answer here is a covalent bond. And let's draw that. So if you have oxygen, it's got 8 pluses. So you can look that up in the periodic chart if you want to, or you can trust me. So the first 2 electrons go here, and then it's got 3, 4, 5, 6, 7, 8. So it's got 2 lonely unpaired electrons, and I'm going to draw it with another oxygen. So it's got 2 electrons in the first shell. This should say 8 plus, 8 positives. So your protons go in the nucleus. The electrons buzz around outside of the nucleus, and so they're going to be even. So if there's 8 pluses, you're going to have 8 minuses unless something has happened, like a chemical reaction, like if it lost or gained an electron. But anyway, for now, we're going to draw them neutral. So that's 1, 2. We're going to need to get up to 8. So that goes 3, 4, 5, 6. Remember, fill in the first 4, and then you can double them up. So that would be 7, that would be 8. So this one has 2 lonely electrons, and this one has 2 lonely electrons. So they're going to share, and these electrons will spin around both of them. And these electrons will likewise spin around both of them. So they are sharing electrons, and it's a very, very strong bond, and that's a covalent bond. I think I mentioned to some of you a way to try to remember that. Co means 2, usually, or at least like there's 2 things working together. And veil is what a lady wears sometimes when she's getting married. Oh, so happy. Those are her arms. And her pretty wedding dress. And her hair, maybe up in a bun. And sometimes a lady will wear a veil. Oh man, now you can't even see her face. Anyway, spelled a little bit differently, but this thing is what she wears on her wedding day when she gets married, and marriage is supposed to be a very strong bond. And covalent bonds are very strong bonds caused by electrons actually being shared. It's not like one side, um, it's not like one side of a molecule is attracted to another side of a molecule and there's like this little weak bond. Covalent is when they actually share these electrons. So you have electrons that spin around both of them. That's a very, very strong bond, and that is covalent because the lady getting married, getting this strong bond, wears a veil sometimes. Okay, so now we're talking about water, the hydrogen atoms of a water molecule. So let's look at that. Here's water. And this is a strong bond that holds water together, that holds the hydrogen to the oxygen and the oxygen to the other hydrogen. There's a weak bond that happens between different water molecules, and that's because there's a partial negative charge here and a partial positive charge over here. And for this one, it's got the partial negative and the partial positive. So if you remember our whole discussion with polarity, water molecules are these polar molecules. That means they're different. They have one side that's sort of negative and one side that's sort of positive. So the interaction here between this water molecule and this water molecule is called a hydrogen bond. But the interaction between this oxygen and this hydrogen is very strong. That's a covalent bond. So that's a strong bond. This bond in here is a weak bond. And if you, I can draw that out maybe a little bit better for you. So here's oxygen. It's got 8 pluses. 1, 2 in the first shell. 3, 4, 5, 6, 7, 8. So here's a hydrogen. It's just got 1 proton. It's got 1 electron going around in this circle. And these two share an electron. There'll be another one too, another hydrogen, and this one will share its electron with that one. And so the electrons will go around both, and these electrons will go around both. The difference is that if you're this little tiny electron, are you going to be more attracted to the 8 pluses here or to the 1 plus down here? And the answer is you're going to be more attracted to the 8 pluses. So you're going to spend much more time here and then come here once in a while and spend much more time here and then come down here once in a while and then spend much more time over here and then come down here once in a while. So although you have 8 pluses, you probably have more like 8.5 minuses over here. So this side ends up being more negative. So anyway, because they're sharing, it's a strong covalent bond, and it's polar, meaning the electrons spend more time here than they do here. So within a water molecule, the hydrogen atoms of a water molecule are bonded to the oxygen atoms by this strong polar covalent bond. So we can already cross out these. And I would recommend that you actually write all over your tests and cross out the ones you know are not true. Whereas the neighboring water molecules, that means this one's a neighbor to that one, are held together here by this weak bond. It's called a hydrogen bond. So the answer there is A. An electrically charged particle is called, this is a definition that you absolutely have to memorize, it is called an ion. I haven't talked about isotopes this year yet. We'll talk about them in January or so. Atom is neutral and a molecule would be neutral unless you could call it an ion if it gets charged. So that this is a definition you have to learn. An ion is a charged particle. It's either positive or negative. Household ammonia has a pH of 12. Let's do our chart. I always do these. So this pH scale goes from the 0 to 14 with a 7 in the middle as neutral. And whenever you do the pH, you gotta sing your song. A, B, C. Okay, so A is for acid, B is for base, 0 to 7 is an acid. So we're talking about household ammonia with a pH of 12 and household bleach with a pH of 13. Which of the following statements about them is true? Anytime it says bleach is a stronger acid, well, I know 12 and 13 are way over here, they're bases. So I can get rid of any of the acid ones. Here, whoops, oh my goodness. I didn't mean for that to happen. And I'll get rid of this acid one. This one says bleach and ammonia are both close to neutral. Well, neutral's here, and these are way over here. I'm going to say no way. And so now I'm between A and C. Bleach is a stronger base or ammonia is a stronger base. Let's see, ammonia is pH 12. And bleach is pH 13. So they're both bases. Which one is a stronger base? Here's neutral. Whatever's further away from neutral is the stronger one. Because if you're very close to here, like a pH of 8, that's practically neutral. So that would be a weak base. The further over here is a stronger base because you're getting away from the number 7. So 13, which is bleach. So that's A. The electricity of the body is caused by moving, that's moving ions, which is so cool. So electrons are the things that move along wires, that if you've ever done one of these circuits things in science class. You might have a battery here, and the wires will be connected to it, and you might have a switch at some point. But anyway, this should be lighting the light bulb if the battery's not dead. These are moving electrons. So the stuff that moves in the wires in your house and through a light bulb, a regular light bulb, um, would be electrons. Protons are stuck in a nucleus. They're not moving anywhere. Neutrons are also stuck in a nucleus, and they don't have a charge anyway. Ions are charged atoms or molecules. When they move, they actually cause electricity, and that's the electricity of your body. So that's, I think, super, super cool. Calcium ions, potassium ions, sodium ions, chlorine ions, all these things make your heart and your brain work. They're electrical. What are the 6 most abundant elements in the human body? Gosh, this actually isn't a good question. We should say in living things, because in the human body it's actually a little bit different. So the thing I want you to remember is CHOMPS. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These are the 6 most abundant elements in living things in general. In humans, there's actually a lot of calcium, but I don't want you to remember that. What I want you to remember is CHOMPS. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Super important. A hydrogen atom has 1 electron, okay, and like this. How many covalent bonds can it form? Well, it has this 1 lonely electron, and this first shell can actually hold 2, so that means it can bond with 1 other atom. Ooh, that wasn't supposed to go away. Let's say it's another hydrogen atom. I guess that came back magically just in time. So these 2 can share, and that would be 1 bond between them. Because remember, you're only putting 2 electrons in that first energy level. So you're going to make, and they're going to share, right? And so if they share, that's covalent bonds. So it should be 1 covalent bond. It actually can form an ionic bond also, but it wouldn't be 2. So hydrogen, it has 1 proton and 1 electron. If that electron goes away, bye-bye electron, you're left with just the hydrogen ion, just a proton, and that can form an ionic bond, like, for example, H plus and Cl minus form hydrochloric acid. So it could form 1 ionic bond, which I didn't talk much about that, so you don't have to worry too much about that. But the covalent bonds you definitely need to know. And there's really no place where it says 1 ionic bond anyway. You don't really get doubles, so that's kind of weird. Okay, you know that the old cliche, I see. You know that the old cliche, oil and water don't mix, is true. Why? So we did that in lab. We had a beaker and you put water in it and then you dropped some oil in it and they were separate. And so the reason is, let's see, oil is hydrophilic. No, if it were hydrophilic, they would all mix up. Oil is polar and water is not. Well, I think they are opposites because they're not mixing. But is water polar or non-polar? So here's that guy in the fishing boat. Anyway, he's got this fishing pole, or maybe she, and the fishing line, and of course, you wouldn't fish if there were no water around, because there'd be no fish. To think that worm on your hook looked good. Hi, fishy. So water and pole go together, so water is polar. Oil is polar? Nope. Water is polar and oil is not. That looks like our answer. Water is hydrophobic. That's funny because water would hate itself, so that would be bad. So water and oil are different because water is polar and oil is not. Glucose molecules are to starch as blank are to proteins. So glucose are these little molecules. You put them together, they're monomers, and you make starch. So we're talking about monomer to polymer. A protein is a polymer. Let's figure out what its monomer is. It's amino acids. I gotta pause this.